Hello all of you. So in the last week, we have been discussing the basics of the Monte Carlo simulation method. So in this week, we will discuss how do we actually numerically implement that on a computer. And we will first do the basic algorithms, and then we will discuss some of the case studies where we can employ the Monte Carlo simulations. So before I proceed, I want to mention here that all the programs that I will do will be done in the Python language. Uh, if you look at the actual molecular simulation programs, they are mostly written in either C, C++, or Fortran, but Python is much easier to work with. That's why I have chosen Python. But keep in mind that if the efficiency of the program is not so good, particularly for very large systems, then we typically have to move to C or C++, right? But for the purpose of demonstration, I think Python is much easier language. So if you are comfortable with Python, it is great. If you are not very comfortable, it's very easy to learn. You can go to the Python website and learn the basics of the Python language. I will try to go through some of them in the codes that I will discuss, but clearly whenever you are in doubt, you can go to the Python website, and that's a great reference for learning Python. Now there are several development environments in Python. The one I will use is Jupyter, and just like Python, the Jupyter also is kind of open source. You can download for free, and when you download it, you typically download some kind of library of Pythons in addition to the basic Python code. The libraries that I would be using are NumPy and Matplotlib, but there are a whole host of libraries like SciPy and all that. So it's better to get an installation of Python. One of the packages where Python comes packaged with all these libraries is the Anaconda package. You can download on any platform that you have, a Windows, Mac, or Linux, and you should be able to install then the Jupyter Notebook. And typically when you open the Jupyter Notebook, it opens in a browser. That is not to mean that it needs internet to run. It cannot be run offline, but it is just more comfortable to work in the browser. It doesn't have any separate editing thing. You can just operate in the browser. So all the examples I will show you will tend to show in a browser, but keep in mind that the codes you can pretty much code on your computer. I will try to provide the codes later in the course. I will tell you where to get it from. But for the time being, I am pretty much giving you all the code, or at least the code snippets that are necessary for whatever we will discuss. So with this background, let's first start with the first demonstration of the Monte Carlo scheme, where we are not doing thermodynamics, where we are interested in the computation of pi. I already have demonstrated the algorithm for how can I use Monte Carlo for pi computation. Now I want to do the same thing on a computer. So just to quickly recall, the idea was I will look in a unit circle and one quadrant of that, because 4 times that will be the area of the circle. So the area of this thing is therefore pi by 4. Excuse my drawing. So this is 1 here and 1 here. It's indeed a circle, the quadrant of that. And the way the Monte Carlo should work is I imagine a square again of unit length and unit width, and I generate points within that square, and then the number of points that lie within the circle. So number of points in circle divided by total number of points that I generate in the range x going from 0 to 1 and y going from 0 to 1. and that will give me the ratio of the areas, that is pi by 4 divided by 1, that is the area of the square, and from therefore I can get the value of pi. Now let us see how it is done on a computer. So essentially, whenever I start a Python code, I first import all the libraries that I need for the Python code, and there are several ways I can import the libraries. If I am using many functions from that library, I can just import the entire library, something like, let us say I am using a NumPy library. If I say from NumPy import star, I can import the entire library, and of course, as you may expect, since that is ultimately going to be a burden on the RAM of the computer, that is typically not a good idea if you are using only some command in the library. So you can also import particular function. Let's say my code only needs the square root function. I can say from NumPy import sqrt, and now the code can interpret sqrt because it's coming from the NumPy library, right? So only one function. We can add more functions by adding comma, let's say sqrt comma some other function name and so on. And then what we can also do is, and that is necessary for when we are using the code with multiple libraries, because sometimes what may happen is that the same function name is defined in two libraries that you are using. So in that case, there can be a possible conflict. So therefore, instead of importing it as it is, you can import as some particular name. So let's say import NumPy as some name I am giving, let's say NP. So now I am importing the entire NumPy library, but now the functions has to be called by something like np dot square root sqrt for square root. In the earlier case, I could have done simply sqrt and the code will interpret. So by as and a name that I can give, so you can give any name, as I have chosen the name np. So then it is basically imported as some kind of an object, and the functions have to be called from that particular object. So this is a standard coding practice. In most cases, it doesn't make any difference how you are doing it, but just as a good coding practice, I will be using something like that in many cases, or something else that I will show you later. So that is the first thing. So every code doesn't really need libraries. I mean, like if I want to do basic arithmetic operations, even the basic version of Python without any libraries can do that. But if you need some sort of mathematical functions, it is typically essential to use a NumPy libraries. Similarly, when you want to do some kind of matrix manipulations and all that, sometimes you use also a SciPy library. And if you want to do some kind of plotting, you need some plotting libraries. And there are a whole variety of rich libraries. And the good thing is that most of them are open source. So we don't have to pay any money in doing that. So with this particular idea, so if you look in this particular code, I am importing two library, a matplotlib.pyplot, that is for the plotting functions I will use in the code, and I am importing as plt. So I will call the command from the library as plt dot whatever the function name is. Similarly, I am importing NumPy as np. So I will call all the function from NumPy library as np dot something. And then I define numrand is equal to 10. That is the number of points that I generate, right? So clearly you can use any number here. The more numbers you put, you may expect there will be more accuracy, but at the same time, it is going to take more time, right? And but in this particular simple code, you can pretty much do a very large number of points, and it runs within a minute. So then I need to store the coordinates of the points that I generate, right? So in the example I was showing you, so all the points will have some coordinates x, y, let me call it something like xi, yi, where I goes from 1 to n, the number of points. So, I want to store those values, because using that coordinate only I can find out whether the points will lie in the circle or outside the circle. So, therefore, I create an empty array to hold these x and y coordinate values. So, array will contain the coordinates. So, one of the good things about Python is that the flexibility with which we can use the arrays, right. So, if you are used to like a C language, you either define an array size a priori, and if I want to increase the size in between the code, it is quite complicated. You can of course use pointers and all that, that is somewhat better, but of course more computationally more difficult to code. But in Python it is extremely easy, right. On the behind of it, it may be doing something of that sort what C is doing, but when you are coding it, you don't have to really worry so much about all these things. It's much easier in this particular language, that is Python. And if you are also coming from the C background, you may recall that you have to do many includes, has include this, has include that, and so on. That is not really needed in the Python. It is much easier to compile and run, right. Of course, we are calling libraries, but that is of course true. So, that is true also in the C. Let us say I want some mathematical function, I use the math.h library, so I have to include that. And so, this particular import functions are kind of analogous to that. But apart from that, for the basic version of Python, you don't have to do any kind of inclusions and all that. The compiler is much simpler to interpret, both for the user and also on the behind of it. So, then what I really want to do is I want to basically have some mechanism in which I can plot that circle, right. So, I want to basically what I want from here is something that looks like the drawing that I have, that is not necessarily required to do, but just for the sake of plotting, it will look nicer if something like this happens. So, I want to basically show an axis and show this circle, and clearly we know that the circle is given as something like y is equal to under root 1 minus x square. So, in a computer, the way to do it is I will compute y value for many points in the range 0 to 1 and basically plot that array, right. So, that is what I do here. So, I basically compute the y function as sqrt of 1 minus I square, where I is, so this is the definition of a Python array. So, what it tells me is I is going in the range 0 to 1, that is the range, and I am generating 1000 points between 0 to 1. There is no Monte Carlo here so far, I am just plotting the circle. So, I am generating 1000 points between 0 to 1, and the points are uniformly located, and this is done by the linspace function that is present in the NumPy library that I have called using NP, right. And for I in that means I will start with first element of that. So, linspace will give me something like I want 1000 points between 0 to 1. So, 0.001, 0.002 and so on until 1, that is what the array would be. And when I say for I in this, it will, in the first time it enters the loop, it will start from I is equal to 0. Next time it will take I is equal to this, next time it will take I is equal to that, and so on. And for all these cases, this becomes the x value, whatever I pick from here, and the y value I get like 1 minus x square, that is 1 minus I square. And then now once I have done that, so now I want to generate my points, right? And to do that, I again declare two arrays Rx and Ry that will contain the x and y coordinates of the point, right? Before I get there, keep in mind that how the for loop has been defined here. So, I put a column after the for loop, that means that the loop has started, and then this tab that I did or indent I did is very important, because as long as I am indented from the for loop, so this part is indented from the for, I am inside the for loop. As soon as I go back to the same indent as the for, let us say when I come to the Rx, it is in the same line as for, I am out of the loop, right. So, it is much simpler than the C way of doing it, of defining curly brackets and all that. You simply do a tab and shift tab to enter the loop and exit the loop. And also there is an append function that is appending the values. So, I start with an empty array x and y, and I am appending the new value of x as I am going in the loop, and I am running the loop from 0 to 1 for 1000 points. So, it is simply storing the 1000 points in the array. So, at the end of the first for loop, you will have 1000 point array of x and y that represents the circle, the quadrant of the circle. Now, I am starting with the points themselves. So, I declare again array Rx and Ry. This val that I have defined, this will store the number of points in circle, right. So, before starting to generate the points, I set that to 0 just to initialize it, and now every time I find a new point in there, I will simply increment it by 1. That you will see in a minute. So, now I go in the for loop, that is where I am generating my points, and now I am generating for something like an A range of numerand. So, what it does is, since numerand is 10, the number of points that I have started with, what it will do, create an array from containing 10 elements from say 0 to 9, right. So, every time you enter the loop, the I will be the element in the array. The first time it is 0, then 1, then 2, and the last will be n minus 1. So, that will be 9, right. This pretty much tells me that I will enter the loop 10 times or n times, that is the number of points. Now, once I have done that, then I want to uniformly generate points randomly, uniform distribution, but randomly between 0 to 1, and that has been done by the random dot uniform function in the NumPy library that I am calling as NP. So, I generate a value of x and a value of y once in the loop, and then since the loop is done 10 times or the number of point times, this will be done for number of points that I have started with. So, I am saying that the x coordinate is Rxi and y coordinate is Ryi, and naturally I will append that into my Rx and Ry array that is going to contain the coordinates of my x and y points of the points that I am putting in. Now, I want to check whether the point lies in the circle or not, and the way to check it is, if x square plus y square happens to be less than 1, then it is inside, because the equation of the circle is x square plus y square is equal to 1, it is a unit circle. If it is more than that, then we are lying outside. So, outside will be x square plus y square greater than 1. We can say something like that to be precise, but frankly speaking, we are doing in the range 0 to 1. So, that does not really matter. Okay. So, then that is what I check for. This is the condition where I am checking for whether the x square plus y square for the point is less than 1. So, x for a point is Rxi, y for a point is Ryi. the sum of the square is, if it is less than 1, then I mean that I am inside the circle and I increment the value by 1. That is what I am doing here. If on the other hand, if it is greater than 1, that is the would have been the else condition, but I did not write it, then the value will remain unchanged, right. So, either this condition is correct, in that case I increment the value by 1, or the condition is wrong, in case I do nothing, because value remain same as earlier. So, this loop will be run for the number of points that I have, and then in the end I compute the number of points that are inside the circle, that is given by val, divided by the total number of points, that is given by numerand, and multiply by 4, and that will give me the value of pi from the Monte Carlo code. So, with this particular idea, I can then proceed to print the value of pi and plot it, right. So, first of all I am printing the value of pi on the screen, and that is the first thing that will print in here, and then I want to also plot it, right. So, I want to plot first the x and y for the circle, so it will show the circle nicely. Then I want to plot the points, which are the arrays Rx and Ry. I want to plot in the range 0 to 1 in the x, 0 to 1 in the y. We can set the aspect ratio to be equal, and you can also have some title of the plot, some label of x, some label of y, and you can beautify the plot the way you want to be. The key point here is when I am plotting the Rx and Ry, that is the points that I am randomly generating, I am doing with something like a label Rx right here, and that means it is R means red, it is going to be a red point, and X means it will show like crosses on the screen. On the other hand, when I am doing the plot for the circle, I am not putting that thing, that means it will simply plot a line, right. So, you will get a line for the circle and you will get crosses, red crosses for the points that you will generate in there, and then you can also save it, give it some name, save it on the computer, and you can also show it on the screen. Okay, so you have to do the show command, and then only it will show and also save the file there, right. So, you can customize all these things, and I am not going in details here. Pretty much this part of the code remains the same in many functions. Once you know how to plot it, the same thing applies everywhere else. Simply the array definitions will change, the x and y definition will change. So, once we have done that, this is what we get. So, we have plotted the circle. I am doing in the range 0 to 1 in x, 0 to 1 in the y. So, the axis pretty much defines the unit square that we have, and these are the points that I am generating, right. And then I am simply finding the value of pi by counting the number of points inside circle, dividing by total number of points and multiplying by 4. So, in this particular case, if I run for n equal to 10, I get a pi value of 2.8, right. Now, keep in mind that you will not get the same answer if you do it on your computer. Even if you run the same code twice, you will not get the same answer, because every time the code is running, it is generating a new set of random numbers. It is a uniform generator. So, where you generate points will keep on changing as you do the code. So, every 2 runs of the code will not give you the same coordinates of the points, and that is the whole idea of Monte Carlo, that we can pretty much sample the entire region. The points can be uniformly generated anywhere in there. So, you have equal probability to generate point here versus here or somewhere else in the system. So, with this particular idea, keep in mind that you will get a value of pi, and clearly it is not close to 3.14, it is quite far from there. If you run it again, you may get value closer to 3.14 or slightly farther from this, we do not know, right. We can keep on trying, but it is still not too far, because 2.8 is still very close to, I mean, like, it is still close to 3.14. The error is still, as you can say, is around 10% from the value of pi. But now if I increase the n to 100, so clearly we have more points, and therefore we expect that we will have a more accurate value of pi, and that is kind of true. The first decimal seems right, but we are still not there. Maybe that if I run again, I may get 3.1 by, if I am fortunate enough, but still I am not very close to the pi value. So then I can do it for 1000, and now you can see I get the first decimal right. We are getting more points in there. And if I do 10 to the power 4, now the points are pretty much filling that entire square, and then even my second decimal is kind of getting there. It's not 3.14, but it is kind of 3.12. That's close to 3.14 if I compare to something like 3.17 here, right? I keep on doing it, and this takes very less time to run because it's a very simple code. For 10 to the power 5 points, I get both the decimals, first and second decimal right. And if I am doing it 10 to the power 7, then I am getting pretty much all the 3 decimals right. And you see now this entire region is now red, and the reason is because I have generated way too many points. So I have pretty much sampled the x and y space. Now, even though it seems like full, it is not still full, because the markers I was drawing had a size, and that's why it seems to fill the entire regime. Markers were actually points on the diagram. Since I could not generate a point of 0 width, that's why the markers have a finite width. So it may seem like full, but it is not quite full. But we have 10 to the power 7 points. That's the key idea, and that's quite huge. And then the accuracy is also quite reasonable. And this pretty much tells me that Monte Carlo is an efficient way to sample the space. This is not a thermodynamic example, but nonetheless, you see the beauty of the Monte Carlo. I started with randomly generating points, and as soon as the number of points started to increase, I was able to sample the entire region from 0 to 1 in x and 0 to 1 in y. So clearly, the sampling part is quite efficient. We do not expect that just 10 points we can get the correct answer, but with 100 we are quite reasonable, we can say, and with 1000 or 10,000 we are even closer, and beyond 10 to the power 5 we are pretty much getting the 2 decimals or 3 decimals correct. So this is how a Monte Carlo scheme actually integrates performs a numerical integration, and this is what I wanted to demonstrate on how we can use the Monte Carlo for numerical integration. So now I want to come to my next example, and that is the example of a 2-dimensional diffusion. So now we will do a diffusion process, and diffusion is represented as a random walk, right? So we already have discussed the drunkard walk. We were doing a walk in 1 dimension. The drunkard, who is fully unconscious kind of, he is totally forgotten the memory, and now he is making steps randomly to the left or to the right. Now if you imagine the same situation in 2 dimensions, this is a random walk in 2 dimensions, and that is actually representing some sort of a diffusion process. Or you can say this is how the molecules really move. The molecules of particularly the ideal gas, you can see it will move like that. So every molecule is experiencing very frequent collisions, and the collisions appear to be quite random because every other molecule can just come from anywhere with any particular momenta. So the motion of the molecules are going to be quite random. So I am doing in 2 dimensions. You can imagine this represents some sort of a surface diffusion, but now after that we'll also do the 3D case. So what I am doing here essentially is I start with only one particle and I start moving it randomly. So in one Monte Carlo step, I make a movement that is of like a unit length, right? So in this particular case, I am not working in any kind of real units. I am working in some sort of a dimensionless units. So one is the step length, and that is the unit of my system. So I come here, and from there again I take a random unit length step and I come somewhere else. Again I take a random step, I go somewhere else, and I continue doing that. So the step size has been fixed, and this is in some sense representing the trajectory of a single molecule as it is moving in a gas. That is what a diffusion process is. So Einstein has shown that for diffusion processes, there is a very beautiful relation called the Einstein relation that he developed before he got to relativity. He became famous for relativity, but this was one of his first paper on the Brownian diffusion that explained the diffusion process that has been experimentally observed before him. So what he said, that the mean square displacement of a particle in the diffusion process will be proportional to time. In fact, for a general walk in some d dimensions, it goes like 2d dt, where d is my dimension. In this case, it is 2, and d is my diffusion coefficient. This means that if I plot the mean square displacement, I will call it as MSD versus time, we expect that to be a line with a slope of that is proportional to the diffusion coefficient, right. Now, in the Monte Carlo simulation, there is no time, but you may imagine that the steps that I am making are of that unit length, that steps is some measure of some sort of time step that I am making, right. It is not any kind of a real time, to be precise, but that kind of represent something that would also happen in time, because the particles are undergoing a random walk in reality as well. So with that thing in mind, that it is not really true dynamics, we are not doing molecular dynamics simulations, we can still say that if I do a random walk like using Monte Carlo scheme, my mean square displacement is going to be proportional to the number of steps, and the slope, therefore, even if I replace t with n here, that is going to give me some measure of the diffusion coefficient, right. That is the idea, that should always be true whenever we have a diffusion process. That is not completely true if we think about it, because let us say we have a system containing molecule, and for sake of argument, let us say one of the molecules was moving with a velocity v. Now, before it collides with any other particle, it will keep on moving with that velocity v. So, before the collision, the distance traveled will be actually something like v multiplied by t. That will give me an r square that is proportional to t square. So, we can say even on average, my average r square will be going like t square as opposed to going like t. That is what Einstein tells me. But if I am looking at time scales much larger than that, I mean like within the time scale or time step that I am making or step I am making, if many collisions have taken place, then it is no longer true, because if I think of like times tau much more than or even significantly more than the collision time, then in that case, in that tau period, the molecule would have experienced many collisions, and by virtue of which the velocity would have changed many times because of momentum transfers, and this would have changed both its magnitude and its direction, right. So, whatever we have said is actually true when we look in the limit of many collisions, and only then we have r square proportional to t. It turns out that this regime is happening for very small times, the reason being that the particles are really close, the molecules are really close, they will collide in very less time, and therefore, that regime is not extremely important, but it can be important in very specific cases. So, this is what is called a rectilinear motion, and this is what is called a diffusive motion. So, here I am trying to code that in here. So, let us go over this code very quickly. So, now the first two parts were same as the earlier code. I am importing a plotting library, I am importing a NumPy library. Now, we define the number of steps, that is, I will make 10,000 steps in this particular case that I am showing, and I again declare two arrays to contain the coordinates after every step. And let us say if I start from the origin, so in that case I will put the initial value as 0 0 to begin with. Now, I go in the for loop that pretty much runs this code num steps times, that is the number of steps I am doing. Inside that I am generating first of all two numbers x and y between -1 to +1, and then I am dividing by square root of the x square plus y square of that. That will generate basically a step of length unity. So, let us say for example, if I am here, I can pretty much be anywhere on either side. So, I can go towards positive x, positive y, negative x, negative y, positive x, negative y, and whatever. So, therefore, what I am doing is I am generating that x, y in any particular direction, but I am dividing them by something like x square plus y square. And if I do that, then the step length, that is the length of the x, that is now normalized by this, plus length of the y, that is normalized like this. So, square of both of them added together, it is going to be something like that, and that is clearly equal to 1. So, that means sure that I am generating a step of length unity, but since I have generated x and y randomly, that is going to be in any direction from the particular point. So, that is why I am dividing that by norm here, and now I am appending not the x values I generate, but the x value of the previous point plus this x value, the y value of previous point plus this y value, because I am making that step from the previous point to the new point. So, if you remember, this is going to be a Markov process. So, the position at any point depends on the previous point. So, I simply add whatever step I have to the previous coordinates that we have. And now, I go ahead and I want to plot the trajectory of the system. These are very standard plotting commands. So, I will do basically a plot of x and y coordinates as they are moving with time. And what we do see is something like this. So, I am starting from somewhere here, that is my 0 0, and I am making random steps, and now you can see the steps every time are in very different directions. Again, for 10 steps it may look like this, but if I run again it may look like something else. So from anywhere I can go to pretty much in any direction, and that's what is happening here. If I go to larger value of n, trajectory may look something like this. Again, there is no directionality to what we are doing, and we can keep on thinking of even larger value of n, and it is giving you a very interesting to look at trajectories of the diffusion process. So with that point, I want to stop here. In the next lecture, we will discuss how to do the same in the 3 dimensions, and that's where I will also discuss the how to implement the boundary conditions, and then we do some more examples of Monte Carlo simulations. So with that, I want to stop here. Thank you.